Okay, so this week we're talking about Hubble's law, which really it's very hard to underestimate how important this is to modern cosmology. By the way, cosmology is the study of the universe at the very largest scales, the study of what's happening to the universe right now. Is it expanding? Is it contracting? What's going to happen to it in the future? What is the Big Bang? How do we know what the Big Bang was like? All these really big picture questions. And like I mentioned, this is really where my main interests fall, and this is what I worked on in grad school for the most part. So this is it's immensely fascinating things, and we actually are able to talk about a lot of this with not just a little bit of scientific accuracy, but actually with amazingly detailed scientific accuracy. Excuse me. So, and again, Hubble's laws really are founding for how we understand how the universe works today. So it's very, very important. Now, Edwin Hubble, this amazing dude. He started life, he was a state high school high jump champion. He was an amateur boxer, he's a Rhodes Scholar, he coached high school basketball, he went to law school, and not only did he serve in World War I, all of that was before he actually got his PhD in astronomy. So he accomplished all of this when he was even younger than me at this point now. So I kind of feel a little bit ashamed to say that I've only ever done what I've done in my life compared to Hubble. But very, very smart guy in general and very well-rounded. So, you know, if you ever want to read, just go to his Wikipedia page. It's pretty cool to learn about him, or, you know, read a biography of him. So anyway, though, he made arguably maybe arguably along with Einstein, they were actually contemporaries of each other. They probably together made the most important advancements in the history of our understanding of the universe. And so that's what we want to talk about today here. So, Hubble had three main discoveries, and we'll go through each one of these here. You've read about, hopefully, the most important one, Hubble's law, in the book. But let's talk about what he did to get up to that point. So his first discovery was that he was one who really solidified our understanding of how extremely far away these galaxies are. Before his time, we saw that there were these little fuzzy patches of the universe. We didn't know if they were just like little bright patches of clouds in our own galaxy, if they were little groups of stars that were a little further away from most of the other stars we see, or if they were whole other, we called them, one of the postulates was something called island universes. Other entire universes, or what we now call galaxies, that are very, very far away from our universe, which we now call our Milky Way. The terminology wasn't really well defined at that point. But what Hubble did was he confirmed that our galaxy, or what we thought of as our entire universe back then, was just a single galaxy, which was one of many, many, many other galaxies that we can observe today. And so here's a little bit how he did this. He was able to measure the distances of galaxies, and he used what's called the cosmic distance ladder. In your book, I think it's called the cosmic distance chain, but I've always heard of the distance ladder. Anyway, so what we do is we start by measuring small distances. We can actually use radar bouncing off radio signals from here to, say, the moon, bounce off a radar signal from here to the moon and back, and we can see how far the moon is away. Same thing for Venus, same thing for the sun. So we get a scale of how big our solar system is, a relatively small thing. But then we can use that to leapfrog to further distances. So once we start talking about nearby stars, radar stops working. So instead, what we do is, if there's a nearby star, if we stare at that star over the course of 1 year, so there's a star, as we move around in our orbit over the course of the year, at one point in the orbit, we're seeing that star at a certain angle. And then now, 6 months later in our orbit, we're seeing that star at a different angle. So our line of sight to that star changes as we move around our orbit. It's the same thing as, you know, if you hold your index finger in front of your face. If you look at it with your left eye, you're looking at, it's in one position with respect to like the wall. If you look at it with your right eye, it looks like it moves from right to left and back. And that's basically exactly what we're doing. As we're going around our orbit, we're looking at things from one line of sight and then from another line of sight. So right eye, left eye, and so on. And so that's what parallax is. Parallax is seeing how far a star seems to move left and right over the course of the year. And if it moves, let's say, 1/10 of a degree from July until December, or just January, if it moves 1/10 of a degree, we can use that to directly calculate how far away that star is, based on how far we know the sun is away from us. And so we can extend this out to within a few dozen light years away. So at least the relatively nearby stars, we get a very accurate figure of how far away those stars are from us. And then we can use that understanding to then kind of leapfrog up to even further distances, measuring how close, for example, clusters of stars are that are a little bit further away from us than even the Milky Way itself, that are neighboring companion clusters to our Milky Way. We use what's called main sequence fitting. I'm not going to go into the details on that, but just understand that this is a way that we can kind of get intermediate distances a little bit outside the Milky Way. But once we start talking about other galaxies, and this is what Hubble worked on, we use what's called variable star distancing. So what we do here is we've discovered within our own galaxy, there's a whole class of stars that periodically get brighter and dimmer, and brighter and dimmer, and brighter and dimmer. And they do it specifically in a sinusoidal fashion. We can measure it with a sine curve. And what we found out is that for really bright stars, stars that are giving off huge amounts of energy, these stars vary on a very long time scale. It might be a number of years from when they reach their brightest maximum to their dimmest minimum. And so based on how long that time is from the maximum to minimum brightness, we know exactly how bright that star is. Dim stars do this much more quickly. They go from bright to dim, bright to dim, bright to dim on a much more rapid time scale. And so what we've done in our own galaxy is we've been able to calibrate this and say that if we know how long it takes a star to get from maximum to minimum brightness, we know how bright the star is. So here's what we do. Let's say we look at some other galaxy, and we see that there is a star that's varying on a very long time scale. And we can actually see individual stars in other galaxies now. And Hubble entered astronomy at about the time that we were actually able to start resolving individual stars. So he kind of happened to be in the right place at the right time, and also be an amazingly smart guy. But what he did, part of his genius here, was to use this variation in light. So he saw this star that was varying on a long time scale. And he knew that if it was in our own galaxy, let's say if this was, 30 light years away, he knew exactly how bright that star should look. And what he saw was these stars that were varying on a very long time scale were much, 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 much dimmer than any stars that varied on that same time scale in our own galaxy. And what the consequence of this is, even they're varying at the same frequency. And we know that all stars we see in our galaxy have the same brightness, or at least they're giving off the same amount of energy. If this star looks really, really dim to us, what that means is that it must be very, very far away. And he was actually able to use this to directly measure the distance to many of these galaxies using this period luminosity relationship, using these variable stars. And the dimmer they look, the further they must be, based on what we know about how these stars work in our own galaxy. I hope that's clear, but it's actually a really important point, that we use our knowledge of how stars work in our own galaxy and how bright that they should appear to measure the distances to other galaxies when those stars appear much, much dimmer. And so that's basically exactly what he did. And so he categorized the couple dozen nearest galaxies, what we now know are galaxies, and based on how dim those variable stars appeared, he was actually able to give a direct measurement of how far they were away. And so that was really kind of his first main big discovery, that these galaxies, he confirmed that these patches of fuzzy bits of the universe are in fact very far away, and not just little clouds within our own galaxy. So his second discovery was that not only are these galaxies very far away, but they're actually, almost all of them, he found out, were actually moving away from us, which was totally unexpected. Why would we expect that these little patches of things that are very far away wouldn't be standing still? Why would we think that they would be moving? And especially, why would all of these things be moving away from us? Why aren't any or half of them moving towards us and the other half moving away? So here's how he did that. He used something called redshift, which we've talked about a little bit, but just to kind of review it. What the redshift is, it's a form of the Doppler shift. The Doppler shift is the general term for this. Redshift refers specifically to light. But let's say we have a source that's giving off waves. It can be water waves, it can be sound waves, it can be light waves. But let's say that source is approaching a person. So in this case, it's approaching the person on the left with some velocity. As that source is moving towards that person, those waves get squished together. And so this person here on the I guess it's on the right, the person on the right is going to see those waves as being squished together. The wavelength is getting shortened as that source is moving towards him. And on the other side of it, let's say that there is a source moving away from a person. Now as that source is moving away from the person, the waves get spread out. The wavelength gets lengthened. And so the person on the left side here, who's seeing the source moving away from him, is going to measure the waves that object is giving off to have a longer wavelength than they really should be. And that's exactly what we see with light. Turns out that if you have a flashlight that's giving off, let's say only blue light, well, let's say green for the sake of argument. That flashlight is giving off just a very steady green glow. Now, if you move that flashlight very quickly towards someone, those green wavelengths actually get shortened. And what our eyes see that as is the shorter the wavelength, the more blue it looks. So we actually call this blue shifted when we're talking about light waves. When there's something moving towards us, the light waves get compressed, and we see it as bluer light than it usually is. And then the reverse is true if it's moving away from us. Now that the green wavelengths get stretched out, so it might start to look orange or red. And we see that as redshift. And it turns out, the more those waves get stretched out, the faster that object was moving away from us. And this is really important because that's exactly how Hubble measured the velocities of galaxies. So here are a couple examples of spectra from, let's call them individual stars. Now if we see at the top, the top spectra has a couple of these lines in it, a couple of the absorption lines, which are due to specific elements in the atmosphere of that star. Now the middle spectra is the same type of star, so O-type star or a M-type star or something. But that same type of star, it's showing the same exact patterns of lines, except all of those lines are moved to the longer wavelengths. They're moved to the redder light. And so the reason that we know this is, what we know from this is that because those wavelengths are all getting stretched out by the same amount, that star must be moving away from us. So the light that's giving off, when it reaches us, is actually longer wavelengths than what it gave off. And now if we look at the very bottom spectra here, in this case, it's again the same pattern of wavelengths, but now they're moved even further to the red end of the spectrum. They're stretched out even more. And so the star on the bottom would actually be traveling twice as fast, roughly, as the star in the middle that's giving out the spectrum in the middle. The faster it's moving away, the more that light gets stretched out. And there's actually a direct mathematical formula that governs this. It's actually super easy. If the waves get stretched out by 10% from what they should be, that means that star is moving at 10% the speed of light away from us. If they get stretched out by 50%, that means that star is moving at 50% the speed of light away from us. And so just simply by measuring how much the lines from these particular types of stars are being stretched out by, we can directly measure how fast those stars, and therefore the galaxies that those stars are in, are moving away from us. And so that's how Hubble measured how fast those galaxies are moving away. He looked at the individual absorption lines from stars in those galaxies, and he saw that all of them were redshifted to a greater or lesser amount, depending on the galaxy. And so galaxies are really far away, and almost all the galaxies are moving away from us. So two pretty, really important discoveries. But the most important thing was that he actually combined these two discoveries, and he asked, so is there any relationship between how far the galaxy is and how fast it's moving away from us? Now, it's kind of if you had no knowledge of this, you almost wouldn't even think to ask this question, but he did, and turns out he got a really interesting answer. Turns out that the further away a galaxy is, the faster it's moving away from us. Again, this is really important. Galaxies that are further away from us are literally moving away from us at a faster rate than nearby galaxies. And this is what's now come to be known as Hubble's law. The further away a galaxy is, the faster it's receding from us. So, in graph form, this is what he saw. And this is actually from his original paper, one of the most important papers ever published in the history of astronomy. On the x-axis, he's graphing out the distance to these galaxies as he measured it. He's using a funny unit called parsecs. It's just, a parsec is about 3 light years, but same thing. So he's measuring the distances of galaxies, and on the y-axis, he's measuring how fast those galaxies are moving away from us. And as we see, the further to the left we get on the diagram, the higher those velocities are. And he graphed out a linear relationship. in the history of science, we now think that he might have been a little bit presumptuous here, but we also think he kind of knew what he was, what the answer was going to be before he did this. It's not quite clear that it's an exact linear relationship, but it turns out we've done many more measurements, and it actually obeys a very linear relationship. So this is what Hubble's law looks like on graphical form, and it shows that the further a galaxy is, the faster it's moving away from us. So this has huge consequences. What this means is basically that the further things are away, the faster they're moving away, it means that the universe is expanding. And let me give an analogy here. So I have this really cool kind of a slow-mo video of things, doing things. So for example, let's go right here. And I'm just going to go through this in slow motion. It looks just kind of like a jumbled mess. There's little patches of stuff all around. But let's move forward in this in slow motion. So right now it looks like this. And we're going to jump forward. And let's try that a different way. 1 second here. Okay. So let's try this in slow motion. I'll actually just play it. And watch what happens as we progress in time here. The individual droplets of whatever this is, watch what's happening to them as time progresses here. They're moving away. They're moving away from each other. And in particular, watch again. Watch how the droplets on the left are moving compared with the droplets on the upper right, compared with these over here. They're all moving away from each other. The ones over here are moving this way. The ones over here are moving this way. The ones down here are moving this way. But one more time, watch how, for example, a little droplet out here, how fast that's moving compared with the little droplet in here. Or, if you want to go on this side, how a droplet right here is moving compared with the little droplet right there. Watch how fast those things are moving with respect to each other. We see that the further away those... Oops, I'm out of hard drive space. We see that the further away these droplets are from what we're calling the center here, the faster they're moving away from it. So, this, one more time, watch stuff that's near the center versus stuff that's near the outside. The stuff that's near the center isn't moving away very quickly. The stuff that's near the outside is moving away very fast. And there's another... So, by the way, this is exactly what Hubble described. The things that are near to us are moving slowly. The things that are far away are moving quickly. There's another example of this that we're all familiar with. When you watch a firework explode, the little bits and pieces of the shell of that firework, when they explode, they get thrown away at very high velocities. But now if we watch the little streamers that are moving relatively slowly, those ones are much closer to where that firework initially exploded. So the further away the streaks of light are, the faster they're moving. And the closer to where that explosion happened, the more slowly they're moving. So basically the universe is exploding, is kind of what he said. He said it a different way. The universe is expanding. There was some explosion. And after that explosion happened, it began expanding exactly the same way that firework works, exactly the same way that any sort of explosion works, where stuff close to the center is moving slowly, and stuff far away from the center is moving very fast. Now, one more really important thing here. So what we're seeing today is everything is moving away from us. But what happens if we trace this backwards in time? So this is why this video is so useful. Let's trace this backwards in time. We see again, even if you just accept what I'm saying, that the little bits and pieces of whatever this is are moving away faster the further they are away. If you just take that for granted, watch what happens when we play this in reverse here. So I'm going to play it in reverse, and it turns out that if we reverse that expansion, it turns out that everything is coming towards the center, and everything, if we trace back far enough, everything seems to be coming to the same point at the same time. Turns out, hey, it was pineapple. But that's exactly the consequence that Hubble recognized immediately. I'm going to try to go back to my PowerPoint here. Okay, so yeah, this was exactly Hubble's extreme ingenuity. He saw that not only is everything expanding or moving away from us faster the further away it is, but if we play that in reverse, the very far away things would actually be moving back towards us the most quickly. the nearby things will be moving towards us more slowly, again, played in reverse. So, if we play it in reverse, it appears that all of these galaxies are converging in on us. And the particular way that they're converging, the very far away ones, have a lot longer distance to go, but they're also moving a lot faster. And the nearby ones don't have nearly as much distance to get back towards us, but they're also going much more slowly. So it turns out that every single galaxy looks like, when we play in reverse, it looks like they're all converging to the same exact point in space at some point back in time, at the same point in time. That's exactly what the Big Bang is. The Big Bang is simply just the moment in time in which all of those galaxies seem to be emerging at the same point in space. It's not some big, crazy, religious, theological theory. It's simply just the observation that the exact manner of which galaxies are expanding today, if we play it in reverse, all of those galaxies seem to be coming from the same point in space at some instant in time. And it's that instant in time, again, that we call the Big Bang. Again, it's really simple. We just trace things back, everything seems to be coming to the same point in space. And that is the Big Bang. And what we know is that after that, so let's go talking about it in forward motion again. So after that Big Bang happened, after all those galaxies were at the same point in space, for whatever reason, they began expanding away from each other. If you want to think of an explosion, that's fine. The analogy breaks down, I'll get into why that is in a second, but just imagine that there was a huge amount of matter compressed into a very tiny volume of space at some point way back in history. If we exploded that little tiny bit of matter, everything would start expanding away. The stuff that got blown away the fastest, we now, 14 billion years later, see that as moving away from us still, continuing to move away the fastest. The stuff that started expanding at only a small rate, now we're seeing as relatively closer to us and expanding, moving away at a slower rate. So we're actually, Hubble's law is actually a natural consequence of a Big Bang happening. It almost implies, if Hubble's law is true, if faraway galaxies are moving fast, nearby galaxies moving slow, it almost automatically implies that we had some moment of time that everything went bang, if you will. And it really is a simple idea. It's not a religious, it's not an anti-religious, it's not anything that it's made out to be. It's just simply an observation of how the galaxies are moving away from us. And I think that's really important. So, I hope you have questions about this. And I'm actually going to predict a couple of the questions that you may have. I get the same ones every time I talk about this, and I think they're great questions. So let's go through. First of all, so if we're seeing everything moving away from us, if we appear to be at the center of that explosion, does that mean we're at the center of the universe? And the answer here is no. Turns out that no matter what galaxy we're on, we should all be seeing the same exact thing. Every galaxy would say that every other galaxy is moving away from it. So some other alien on the Andromeda galaxy would be seeing the same exact thing as we are, except from their point of view, they would, well, the Andromeda, that's another story, but they would see us moving away from them versus them moving away from us. I have an analogy here. This actually might show this a little better. So we have a whole string of, it's a rubber band with some different colored paper clips attached to it. And let's concentrate on the yellow one. Here, one second. Okay. Let's concentrate on the yellow paper clip in the center. And I'm going to stretch out this rubber band. And watch how these other paper clips or galaxies move away from that center paper clip. So we're seeing that the nearby ones are moving away kind of fast. I'll do it again here. Might be a little tough to see, but the nearby paper clips are moving away kind of fast, and the far away paper clips are moving away faster. Now let's shift over one. Let's go to the black and white paperclip right next to it. Now watch what happens from that black and white paperclip's point of view as I stretch this out. That black and white paperclip is also seeing all those galaxies moving away in exactly the same manner that that other one was. The nearby ones are moving slowly, the far away ones are moving fast. Now let's shift to the one at the end, the red and white paperclip. Same thing here. When I stretch it out, the nearby galaxies are moving away slowly, the far away galaxies are moving away fast. You might not be able to see that. So no matter which one we do this from, each galaxy is seeing the same exact thing happen. They're seeing the nearby galaxies move slowly away from them, and the far away galaxies moving fast. So really, every galaxy can think of themselves as the center of the universe. Or we can just say that there is no center of the universe. That if the universe is expanding at the same rate everywhere, every single galaxy should say that they're seeing the same thing. So we're not the center of the universe any more than anyone else is the center of the universe. Okay, the next question. So what's the universe expanding into? So this explosion happened. Let's use the pineapple expanding analogy. The pineapple exploded. Before the explosion happened, the pineapple was occupying a small volume of space. When that pineapple exploded, it expanded to fill up more and more space around it. So if that analogy is true, what does that say about the universe? When the universe went bang, it was small, and then did it expand to engulf more and more space? Turns out that that's not true. That this is where the analogy breaks down. Because the universe includes all of space. It makes no sense to talk about a region of space that's not already a part of the universe. Oh, I'm going to erase that for 1 second here. So when the universe started expanding, it's not like there was extra space left over that it could expand into, because the universe, by its definition, essentially, includes all of space. So the universe, if the space was out there, it was already part of the universe. It's not like the universe can expand into that extra space. So what we mean when we say the universe is expanding is that the distance between objects is getting further. So at some point back in the history of the universe, we could imagine that all the galaxies, or all the galaxies were much closer together, much more tightly packed. As the universe expanded, those galaxies got further and further apart. So that's one way of talking about an expansion. Things are getting further and further apart over time. We don't have to worry about what's happening at the edge of the universe. In fact, we think the universe, basically one of the best ways to define what the universe is, and I think Carl Sagan coined this, it's all that ever was, all that ever is, and all that ever will be. And that includes all of space. So when the Big Bang happened, the universe included all of space. It already included all space. But the difference was, in the universe at that point, everything was much more tightly packed than it is today. Over time, that universe, which again included all space, if you look at the relative distances between little points in the universe, those distances got bigger over time. And the correct interpretation that we now have of the expansion of the universe, we can't think of it in terms of like a pineapple that started engulfing only a small region of space and expanded to include more space. The better way to think of it, and actually the correct way to think of it now, is that the space in between, or the space in between galaxies is actually stretching out. Or that space itself is expanding. Space itself is stretching out. And that's what we mean when we say the universe is expanding. It's not that it's expanding to fill up more and more space, because it already included all space. It's simply that the space itself is stretching out. And so that's why we see the galaxies are getting further and further away, because the space between us and other galaxies is literally stretching out. And again, this is actually the way that we need to view this, because this is how, among other things, this is how we can see a redshift greater than 1. Forget what I just said. If you want to email me about what that means, please do, but I'm not going to elaborate. But this really is why the universe is actually getting bigger. It's that space itself is stretching out. So, the last question is, and I get this all the time, so, we understand, we can trace back to the Big Bang, we see that all galaxies are coming from the same point in space, so what happened before the Big Bang? What can we use about what we see today, about our very detailed knowledge of the Big Bang, to predict what happened before and what caused it to go bang? So the analogy I'm going to use here is, when we talk about galaxies moving away from us, let's say we see one galaxy to our east and one galaxy to our west, and we see how fast they're moving away. It's the same exact problem as there's a truck, or 2 trains left Chicago, one going east, one going west. If we know how far away they are from each other, and if we know how fast they're moving away, we can trace back in time and see exactly when those 2 trains left the station in Chicago. So, those of you guys who have taken a physics class, you've probably all heard this problem. 2 trains leave, Chicago, they're X distance away, they're moving however fast. How long ago were they actually at the same point in space? That's exactly the question we're answering with the Big Bang. But I guarantee you, those of you guys who have heard this question in high school physics class or whatever, I guarantee you were never asked the question, what were the train conductors doing before they left the station? There's no way, based on their velocities moving away now and how far they are away, there's no way we could ever possibly answer whether those train conductors were drinking coffee or reading a newspaper or whatever. All we can answer is what happened just after they left the station and how the trains advanced away from that station after they left. We can never answer what happened before the conductor got into the car. And that's the exact same thing with asking what happened before the Big Bang. Because our understanding of the Big Bang comes from entirely what we see as the aftermath of the Big Bang. Things are moving away. There's no way, even if we can trace back to the instant of the Big Bang, there's no way we can understand what happened before the Big Bang with only our knowledge of what's happening now. And so in science and in cosmology, in astronomy, we simply cannot answer the question of what happened before the Big Bang. And if anyone tries to ever tell you that, oh yeah, science says that before the Big Bang this happened, just stop listening to them right there, because based on every bit of evidence that we have and every bit of observations, theories, we simply cannot possibly predict what happened before t equals 0, before the Big Bang happened. And by the way, going into a little bit of theology here, this is one of the reasons why personally I think that religious theories and scientific thinking aren't so mutually exclusive, that science answers the question of what happened after the universe began expanding. Religion, very naturally, you could ask what happened before. There's no way science can answer what God was doing. If there was, if God is one who said, "Okay, universe, go bang," religion can ask what God was doing before the Big Bang happened. But there's no way science could ever ask or answer that. So, just as an aside, I hope this makes sense here. And again, we're talking about really big questions, but I do want to stress that we actually do have very rigorous scientific analysis and observations and experiments to actually confirm that these are what we think is actually exactly how the universe is operating today. So the last question, and the really big question, how will the universe end? I'm going to leave that for next week.